Assalamu alaikum and welcome to lecture number 24. In this lecture we are going to discuss about the IIR and FIR filters, and we also discuss about the filter design steps, that how many steps are there to design a filter. Okay, so digital filters can be broadly divided into two main classes or two main types, that are IIR filter or infinite impulse response and FIR filter or finite impulse response filters. The input-output relationship for the IIR filter is given as this one, and you can see this is basically a convolution. So this IIR expression can also be expressed in recursive form. So we can write summation k running from 1 up to n, aky of n minus k, plus summation k running from 0 up to m bkx of n minus k, where ak and bk are the coefficients of the filter. The resulting system function for the IIR can be written as h of z. You understand, you take the z transform of this and you get the resulting expression. Okay, so I hope you are quite familiar with this expression, because many of the times we have done this before, so it shouldn't be an surprise for you. Whereas in case of FIR filters, we have the expression summation k running from 0 up to n minus 1, h of k x of n minus k. So we can also find the z transform for the FIR case. If we have impulse response h of k, then h of z will be equal to summation k running from 0 up to n minus 1, h of k z power minus k. So after defining the FIR and IIR, then the question is, what should we use? Should we use FIR filter for our filtering operation, or we should go for the IIR filters? So to answer this question, we can compare the strength and weaknesses of the two filters, which are summarized here. So we use FIR filters when we need exactly linear phase response. So that means there will be no phase distortion introduced into the signal by the filter, and this is an important requirement in many applications. In contrast to the digital analog, where we have infinite values, Each coefficient can have infinite value, or similarly the signal can have infinite values. In digital we have limited values, that is we represent each analog value by a limited number of bits. So it will cause the quantization noise and those type of things. I hope you understand, because we have also done this so many times. So you have the understanding that in case of digital we have finite number of bits to implement. So that means we have to represent the coefficients of the filters by finite number of bits, and also the sample value, or the value of the signal, should also be represented by finite number of bits. So in such case we have a rounding of noise, right, and the quantization errors. So based on these we see that in case of FIR, their effect is much less severe than in IIR. The second thing, the fourth point is that FIR filters require more coefficients for sharp cutoff filters than IIR. Thus, for a given amplitude frequency specification, more processing time and more storage will be required when you implement FIR filter. Or in case of IIR filter, we will require less processing time and less storage. So that's a plus point of IIR. However, one can readily take advantage of the computational speed of FFT and multi-rate techniques to improve significantly the efficiency of FIR implementation. But however, this is the fact that FIR will require more computation and more storage in comparison with the IIR. Also, analog filters can be readily transformed into equivalent IIR digital filters meeting the similar specification. So in case of FIR, this is not possible as they have no analog counterparts. In general, FIR is algebraically more difficult to synthesize, whereas the IIR filter can easily be made. So from the above discussion, we can say that we should use IIR when the only important requirement are sharp cutoff filters and high throughput, as IIR filters, especially those using elliptic characteristic, will give fewer coefficients than the FIR filter with the same specification. Use FIR if the number of filter coefficient is not too large, and in particular if little or no phase distortion is desired. In case of FIR, we also have new DSP processors that have architecture which are tailored to the FIR filtering, and indeed some are designed specially for FIR. So this problem might be overcome. To get clear understanding of the FIR and IIR, let's have an example where we are given a transfer function h of z equal to this one with given coefficient values of these, and h of z with this one with given coefficient values. So both of these filters, right, h of z this one and h of z this one, they have identical amplitude frequency response specifications. So let's compare the two and let's see which one is better. Okay, so we have to find in this example whether it's an FIR or IIR. So for sure you understand this is an IIR system. It has poles and zeros, whereas in case of IIR we have only zeros, with the exception that it has a pole when z equals to 0. So we have to represent the operation in the block diagram and write down the difference equation, and in part C we have to determine and comment on the computational and storage requirements of the two. So you understand that's quite straightforward. We can represent it by block diagram or signal flow graph. So you understand these are your zeros and these are the poles. So you're well familiar with it. So the resulting structure for the this will be this one. I hope I don't have to draw it because you're very well familiar with it. So you can see it's direct form 1 implementation, right? In direct form 1 you have zeros followed by the poles. Is it? Or it's direct form 2 implementation. Okay, so it's basically direct form 2, or maybe we just think which one it is. Okay, anyway, so this is the resulting expression for the system function given by the equation 1, and the system function given by equation 2 is plotted here. So I hope that's a very straightforward thing how to plot these. Okay, so if we can write the difference equation. So W of n, if you look at this one, has two inputs, x of n and this one. So we have x of n, and then we have the I hope the notation is not confusing for you, because previously we were following the book of Oppenheim. There we represented the coefficients of the poles by A and coefficients of the zero by B. But here this we are, as I talked to you in the previous lecture, that we'll be following the book of Digital Signal Processing, a practical approach by Emmanuel, a feature. So there it's quite, I think, a different approach, because here the coefficients of the zeros are represented by A and coefficients of the poles are represented by B. So maybe this is not confusing for you, right? So straight away if you place the values, then you can just have values instead of A and B. So anyway, so these are the W of n. So W of n, if we look at the block diagram, we can see W of n equals to x of n minus, right, B1, right, and you have one unit delayed, so B1 Wn minus 1 plus minus B2, so minus B2, one more unit delay, so minus B2 Wn minus 2. Similarly, the expression for y of n is y of n equals to a naught times scaling, so we'll have Wn scaled by a naught time plus this is Wn minus 1, which is scaled by a factor of a1, so it is plus Wan minus 1, and again one more unit delay in Wn, so here we'll have a signal that is Wn minus 2, and we are scaling it by a factor of 2, so we'll have this equation. Okay, similarly for the case of the FIR, so we have input signal, okay, and which is scaled by h of 0, then we delay the input signal by 1 unit, right? Or you can just open the equation, and I hope you can easily make this diagram. I think for sure we have done this one also while we were doing structures, so I hope it should not be an issue for you. Now if we look at the number of multiplications required in each case, so for the multiplication, you see x of n is multiplied by h of 0, then x of n minus 1 multiplied by h of 1, h of 2, and so on up to h of 11. So we have 12 multiplication here, right, ranging from h of 0 up to h of 11, so 12 here. Now if we look at the IIR system, so we have one multiplication here, one here, 2, this one 3, this is 4, and this is 4, 5. So this required 5 multiplications. So in the expression you're told that both the filter meets identical amplitude frequency responses. So that means they both have the same frequency amplitude response. So that means you can implement any of the two. But by looking at number of multiplication required, in case of FIR we need 12, whereas in IIR we need 5. So definitely the system with fewer, we will like to have system that requires fewer multiplication and fewer storage. Also, number of addition required, here we have to add 11, right? H of 0, x of n plus x of n minus 1, h of 1, and so on. Similarly, in case of the IIR system, we just need 4 addition. Okay. Again, the storage location required, so we need the storage locations for the coefficient storing and the data storing. Okay, so we required 12 storage locations for coefficients, and similarly we need the 12 storage location for storing the data. So that means 12 plus 12 equals to 24. Whereas in case of the IIR system, we just need the how many storage locations? So we need 5 locations, right? 5 for the coefficients. And how many additions are there? Okay, so we have 3 addition. So okay, so I leave it to you. Anyway, it will be 4. Okay, so 4 addition we required. So the total number of storage required is 8. Okay, so I hope you get the idea that based on the required number of multiplications, additions, and storage location, the IIR system is much more efficient than the FIR system because it requires a lot of resources. So the next topic we are considering is the filter design steps. The design of a digital filter involves these 5 steps. In the first step, we give the specification of the filter requirements, that what type of filter we need, what are the frequencies, and so on. We'll talk in detail. So the second step is the calculation of, once we find the specification, the second step is then to calculate or approximate the coefficients. The third step is representation of a filter by suitable structure. I think you have understanding of the that we also call it realization by structure. So you understand that what is the structure, and I think you have well understanding of the different type of structures we have. The fourth step is the analysis of the effects of finite word length on the filter performance, and the fifth step will be implementation of the filter in software and or hardware. These specifications are normally specified in frequency domain. For the frequency selective filters such as low pass filter or high pass filter or band pass filter, these specifications are in the form of tolerances. So the main parameters are the pass band deviation, stop band deviation, pass band edge frequency, stop band edge frequency, etc. Whereas the phase response is generally not specified. In many cases, it is sufficient to indicate that whether we need whether the phase distortion is of concern for us or not, or whether we required a linear phase response. So comparing with the ideal filter, so you can see this is a ideal low pass filter. So in pass band there are no ripples, we have just a flat, okay, and the response becomes 0 when the input frequency is greater than or equal to the cutoff frequency of the signal. You understand the frequencies are in the radians, right? We can also have the linear frequency. You understand the relationship between the linear and the angular frequency or frequency in radian. That is, you just multiply the linear frequency f. So you understand the linear frequency has units of hertz, so hertz can be converted into radians by simply multiplying with 2 pi. So the non-linear frequency or the angular frequency is represented by omega, whereas the linear frequency is represented by f. So this is the case. The ideal low pass filter. Similarly, for the case of ideal high pass filter, we have response something like this. This is the another type of filter which we call it a band pass filter. So it has response which is 0 when the input signal frequency is less than the lower cutoff frequency, or when the input frequency has values which are greater than the upper cutoff frequency. If the frequencies are between these, then only those signals will be passed. So this is an example of the ideal band pass filter. Similarly, this is an example of the band stop filter. All those frequencies which are equal to or greater than this lower frequency are equal to or less than this. That means between these frequencies, this filter will suppress these values, right? So if the input signal has frequencies say 0 to pi, then when we use this filter, the output of the system will have frequencies between 0 to WD and A and WB to pi, whereas in between these frequencies they will be stopped. Now for the case, this is the these are the representation of the frequency response for the ideal case, but practically we don't have this sharp transitions. Instead we have not only ripples in the pass band, like okay, this is the dashed line represents the ideal filter, whereas the solid line represents the actual or practical filter. So if we compare the two, we can see that in the pass band, again we don't have a flat response, we have some ripples here. Similarly, if we compare with the stop band, so it's not straight away. That means that if the frequency is less than omega c, it will be 1, and if the frequency is greater than omega c, it will be 0, like here we have. So it's not the case, rather it will have a gentle transition from high towards low or towards 0. And also we will have this this is a stop band. Also in the stop band we have the ripples. It's not like this one. So in case of ideal, we have two bands. One is the pass band, this one. I'm talking about the low pass filter, right? This is an example for the low pass filter. Similar figures can be drawn for the other types, high pass, band pass, and so on. So in ideal low pass filter, we have two bands. That's the pass band and the stop band, right? But in case of practical filters, we have three bands. That is the pass band, then we have a transition band, and then we have the stop band. So I hope this gives you idea. If you have any question or anything you want to add or discuss, we can discuss it in the live session. The stop band and pass band deviation may be expressed as ordinary numbers, or they can also be expressed in decibels. Okay, so in decibels, you understand, you're not new to this one, so you just multiply it by 10 and then take the log. So for the square case, we have we multiply it by 20. So in this case, because it refers to the attenuation, so we'll multiply it by -20 log of sigma s, you understand, is a stop band attenuation. Similarly, pass band, we use 20 log of 10, 1 plus sigma p. So before moving further, let's have an example. So for example, we need to design an FIR band pass filter with the following specification. So we have the pass band. So pass band is 0.1 to 0.33. You understand this is normalized. That means these are the digital frequencies, and you obtain this by dividing the given frequency by the sampling frequency. We are also given the transition width, that is 0.4. Again, this is normalized, and we are given the stop band attenuation, which is 0.001, and pass band deviation, which is 0.05. Now we have to sketch the tolerance scheme for the filter. So the tolerance scheme for the filter is that you draw its pictorial representation, and you see how it is different from the actual. So that's your ideal, and this is your actual, right? So these are the lower cutoff frequency and upper cutoff frequency. So based on this, we plot this one. So that's your cutoff pass band. Okay, now we are given transition width, so that is 0.04. so that means from 0.33 plus 0.34 will result into 0.37. At 0.37 onwards we'll have stop band, and similarly 0.18. so if we subtract 0.04 from it, so you'll get 0.14. so now this is the transition band. So we want to have this transition band as small as possible, because if the transition band comes to 0, that means we are actually near to the ideal response. Okay, so that's a graph for this one. Then the next step is the express the filter band edge frequencies in the standard units of kilohertz. So I think you understand, from normalized into standard units you can straight away go easily, because you get the normalized by dividing the frequency by the sampling frequency. So if you have sampling frequency of 10 kilohertz, then we'll do the opposite. That means we'll multiply them with the sampling frequency to get the standard units of hertz or kilohertz. Okay, so that means if I multiply 0.18 by 10, so I'll get 1.8. so we have the pass band of 1.8 up to 33 kilohertz. You understand that we use digital filtering for the digital signals, and we also can use the digital filters for analog signals. So you understand that signals mostly are analog in nature and our systems are digital. So what we do, we convert or transform the analog signal into digital. You understand the steps involved. So we have this one, the pass band. Then we have stop band is to this side, so it will be 0 to 1.4 kilohertz and 3.7 to 5 kilohertz. That's the stop band for to the right side. Now for the stop band attenuation, we have 0.001. so we have the equation, okay, to express the stop band into the decibels. Okay, so that will be roughly this one. And similarly pass band ripple, which is 20 log of 10. I hope these are clear to you, right? So you just sum them and you take log of this to the base 10 and multiply by this, so you get this, right? So we normally express the attenuation or ripples in dB, so that's how you can represent it. I think we have done this previously also in some other topics, so I will not go into detail. Then the second step, once you are given the specification, the second step is to calculate or approximate the filter coefficients. So there are a number of approximation methods available to calculate filter coefficients for both IIR and FIR. Following are the most widely used methods. I will not go into detail of them because in the following weeks we are going to talk about in detail about these methods. So that is for the case of IIR, we have impulse invariant method, we have a bilinear transformation method, and we have a pole zero placement method. These are the most widely used method for IIR system. Similarly, for the FIR, we have a window method, we have frequency sampling method, and optimal method. So we'll talk about it in the following weeks. Maybe. The third step of the filter design is representation of the filter by suitable structure, or we also call it by realization. So we can realize it using different structures. Again, you have done this topic also, so we'll not go into much detail of this one. And you understand that this will be involved in converting a given transfer function into a suitable filter structure. So that can be a block diagram or it can be a signal flow graph, which are both of these are most widely used to depict the filter structures. Okay, in general, you understand that's the generalized linear constant coefficient difference equation. So based on this equation, we can find the system function, which is something like this. Okay, so based on the expression for the system function, whether it's in a rational system function such as this one, or it is factored system function, or it is in the partial fraction form. Okay, so you can this equation can be used to represent the direct form 1 or form 2 implementation of the structure, whether you use block diagram or signal flow graph. I think that's straightforward and you have done this right. Similarly, we can also represent the system function as a factored form, such as second order factors, this one. So we can express it like this one also, and we can express it this one. So that means depending upon your system function expression, you can make the or draw the block diagram or signal flow graph with, right? So in this case, you have a direct form. Here you will have the cascade form. Okay, you, for example, cascade of second order this one represents, so you have one cascade depending upon how many factors you have. And similarly, this one is the partial fraction expansion, so that means the resulting form will be as a parallel. Okay, the fourth step is the analysis of the effects of finite word length on filter performance. So you understand that in digital we don't have the very high precision. We have to represent whether these are coefficients of the filter or they are the values of the signal. We have to represent them by finite word, right? So that means we will just represent it by a few bits that can be 8 to 16. So the effect they will have will be degradation in performance. In some cases, it might make the poles to go out of the unit circle, thus making the if this is the IIR system, then making it the unstable. So designer must analyze these effects and choose the suitable word length for the filter and the input-output samples. So the main sources of performance degradation using the finite word length is the input-output signal quantization, because when you quantize, you have a quantization noise which is non-replaceable. That means it is irreversible. So here we'll have some degradation. Okay, again coefficients. So theoretically we say we have coefficients with uh, very high precision, or it can have infinite values, but practically we have to represent these coefficients by some finite number of bits, so it will result into some degradation. Again, the arithmetic round of errors will be there. Okay, and the other error includes the overflow error. So the final step in filter design is the implementation of the filter, either in software or hardware. Okay, so before doing the implementation, we need to verify that based on the given word length, does the performance is in acceptable range, or it is not doing what it is supposed to do. That means its performance is severely degraded. So in that case we have to modify the word length. We have to increase the number of bits so that we can bring the performance to an acceptable level. So the implementation can be a software routine or hardware implementation, right? And you understand in digital filters we have three types of operation, that is multiplication, addition or subtraction. You understand same thing, right? So multiplication, addition and delay. So to implement a filter we need the following basic building blocks. We need a memory like ROM for storing the filter coefficients. We need memory like RAM for storing the present and past values of the input output. And we need hardware or software multipliers, and we need adder or arithmetic logic units. So let's have an example. Okay, so we need an analog filter, right, to be converted into an equivalent digital filter that will operate at a sampling frequency of 256 Hertz. The analog filter has the transfer function h of s equal to this one. Now we need to obtain a suitable coefficients for the digital filter. Second, assuming that the digital filter is to be realized using cascade structure. So draw a suitable realization block diagram and develop the difference equation. Then in part 3 we have to repeat for this step 2 for the parallel structure. So you understand that based on the system function you have, you can express the system function as a rational system function. Okay, in which case you have to implement it in form 1 or form 2, or you can have you can express the system function as a in the factor form. In case of factor form, then we can represent or draw the realization block diagram in cascade form. Okay, and the third thing, you have studied all of these things you have done. So in the third case is when you express the system function as a partial fraction expansion. In that case we can have a parallel form. So the first thing is that we have to obtain the filter coefficient. Okay, so these are the continuous time filter or analog filter. So to find the filter coefficients from this analog filter, we can have different options. So one of them is the bilinear transformation. Unfortunately you haven't studied about this one, so we will not spend time on this one. I'll just straight away write this equation, and in the following weeks we'll be talking about this transformation. Okay, so if we apply the bilinear transformation on this system function, we obtain h of z, which is equal to this one. Okay, so again, because we have to here we are asked to realize using the cascade structure. So to realize the cascade structure, we need to express this system function in the factored form. So expressing this in the factored form, we'll get something like this. So now this can be realized in the cascade form. So I hope you understand. If we have now two sections, this one followed by this one, so these are the uh, uh, zeros and these are the poles for the first section, and this is 0 and this is pole for the second section. So I hope you can easily do it. So I leave it to you as a homework. Again, for the parallel structure, we need to express this system function using partial fraction expansion. You know how to do the partial fraction expansion, so using that it will result into this, and now you can see this is a summation, so this can be implemented in parallel structure. Then we have one more problem or example. Okay, so we have a transfer function for an FIR filter, which is this one, and you have to draw the block diagram for this one. So this I also leave as a homework for you. So I think this new topic is quite straightforward, because many of the basic things you have done previously while doing some sampling of continuous time signal, transform analysis, Z-transform, and other topics. So I think this topic should be quite straightforward for you, but still you can ask or discuss as many things, because now many of the concepts should be clear to you, so now you can have a lot of discussion on it. So see you in the live session. Assalamu alaikum.